Let me introduce John Warner quite briefly, and in perhaps an unexpected way. In college, John Warner appeared on the cover of Celebrity magazine because he was actually discovered to be Boston's best and brightest student. In industry, he invented a completely new way of doing chemistry called non-covalent derivatization, and he probably won't spend a lot of time on what that means. But it did help create green chemistry. It's one of the tools that's widely used. Actually, John spent almost 10 years running the research labs at Polaroid. John co-authored with Paul Anastas Green Chemistry, Theory and Practice, which Terry mentioned, which has come to be known as the Bible of the field. While in academia, he was called literally the country's best science and engineering professor, winning not only a presidential award, but an audience with President George W. Bush in the Oval Office to receive the award. And finally, as a small business entrepreneur currently, he has created a game-changing startup, the Warner Babcock Institute, that builds upon green chemistry and is successful from virtually all perspectives and has become so in a short period of time in the middle of history's worst economy. John?
Thank you, Pete. It's an honor to be up here talking to everybody. After listening to Terry, a genius who has created so much of the thinking in this field and the understanding that is the foundation of this whole work in green chemistry, and Pete identifying the environmental health sciences linked to it, it's an honor to be here to be trying to help move this to the next stage. And that's why I think that's the space that I want to talk a little bit about. Is it seems so obvious, it seems so straightforward. What's the problem? Why is it so difficult? Why isn't this just happening? And I think it comes down to if I go to a party, all right, we're hanging around at a party, and everyone's talking, and someone says, "What do you do?" And I say, "I'm a chemist." Talk about a conversation stopper. Immediately the people look at their shoes, they say, "Oh, I hated chemistry in high school." And think about what happens. What are the implications of that application of any relationship to the field of chemistry? I hated chemistry in high school, therefore I know nothing about chemistry. I don't want to know anything about chemistry, and I'm going to live my life pretending it kind of doesn't exist, when in fact, obviously, it's a central science that exists very deeply. And when we have a debate in the public about something being toxic, and someone says, "I hate chemistry in high school," we're kind of in trouble. And I would really argue that that has to be the biggest challenge, because I'm going to tell you a secret. Chemistry is no more difficult than any other subject in high school. I believe it is the most poorly taught, but it is not the most difficult. And that is the problem, and many things spur from that. And so when we talk about what are the greatest challenges to sustainability, and you have some wide-eyed 16-year-old woman who wants to grow up and save the world, do you think being a chemist is the first thing on their list? And if you really think about it, don't we need it to be? Why is it that people aren't doing that? You know, I can remember in high school, you know, someone would come into the room and they would light something on fire in front of of all the kids and say, "Whoa, kids, be a chemist." Okay, you know, I've been a chemist for 30 years. Things exploding usually are not a good thing. You know, why aren't they coming in and saying, "Hey, the world has problems. We need you to solve these problems"? You know, what are we doing wrong? And so really, I think we have to ask ourselves the question about just chemistry in general. You know, yes, we're talking about the molecules. We have brilliant scientists that are doing brilliant things. But we need a lot more people to understand this, and we need to demystify this and bring this to something else. So maybe, just maybe, it's not about how we make molecules, but actually how we make chemists that's the real issue. Okay? And so I'm not some anthropologist that can tell the history of chemistry and things like that. But let me share how I became a chemist, because I think for people who aren't chemists, it might be illustrative. All right. I grew up in Quincy. It's a city south of Boston. I had this massive Sicilian family. My mom had 10 brothers and sisters. I had 35 cousins within a 1-mile radius growing up. And we were plumbers, electricians, and things like that. We had no idea what higher education was. I thought that was when you took a class on the second floor. And I horrified my family one day by saying I wanted to go to college. My father was actually a little upset. He said, what, are you going to be a professional student? Your older brothers have perfectly good jobs. Knock out. So I made a deal that I would work construction full-time while I went to college. But what horrified them more is what I went to college for. I actually went to college as a music major. Oh, my God. And I played in this band called The Elements. Okay, nothing to do with carbon, hydrogen, oxygen. Okay, remember, watch this. I looked at my shoes. I hated chemistry in high school. I was one of them. I had no interest in chemistry. To me, it made no sense. So I went and I became a music major playing in this band called The Elements, which was kind of strange. Things evolved in that, and the tragedy hit in that the drummer of the band ultimately got leukemia, and he passed away over a short period of time. Here I was playing 3 clubs a week in Boston. We had a recording contract. Things were going well, and then fate would have it that it just ended. And as I'm in that moment, I was taking at UMass, you have to take, all the different classes for gen ed, a foreign language, a math class, a science class. Well, as a science class, I really loved biology, and I really loved physics. So I saw if I add them up and divide by 2, I'd come up with chemistry. And I was taking chemistry to fulfill my science requirement. And one day a professor came walking into the lab. He looked at me, said music major, walked right by, and went to the kid next to me and said, would you like to do research in my lab? And he said, sure, I will, Professor Anselm. I overheard the conversation. The kid was my friend. I said, can I come along? And when I went into the research lab, it was like an epiphany happened. All my life, there were 2 people in the world. There were artists and there were scientists. And because I was marginally good at music, I was an artist. And that was what I was, and people who were scientists were scientists. When I got into the research lab and I actually understood what science was all about making things and creating things, it exploded inside me, and I realized that creativity does not know the word art and science. It's a unique human experience. And I even imagined ramming my brain full of electrodes and composing a piece of music on a piano or designing a molecule. And I said, I bet you the same neurons fire. We get it wrong talking art and science and creativity and mixing that up. So once I got that, oh man, did I fall in love with chemistry. I started spending 60 hours a week in the lab, and I spoke in Washington, D.C., I think at 18 years old, about my research. And like Pete said, I was on the cover of Celebrity magazine with Boy George. Pretty weird stuff. And I came to the stunning realization, I have no idea how this happened, but one day I woke up and I said, I'm a chemist. Where did that come from? And so one thing led to another. Next thing you know, I find myself at Princeton University working for Professor E.C. Taylor on anti-cancer chemotherapy. And man, did I have a great time there. I have a record for the most publications as a graduate student at Princeton, published something like 17 papers, worked on the drug that's now called Alimta. It's the most successful anti-cancer drug for solid tumors sold by the Eli Lilly company. Now, I take no credit. It was a massive group of people that worked on it. I did this little part. But it was something that made Princeton very happy. And just to show how weird the world can be, I lost my mom to lung cancer about 10, 11 years ago, and she was actually receiving a derivative of the drug that I had designed 15 years earlier in graduate school. So this relationship between science and society is somewhat mystical. But things went on. Princeton was very proud of me, took pictures of me, and we was holding flags and things like that, and did all these stories about this kid. And one day, a corporate officer from Polaroid, the instant photography company, called me. And he had lunch with me, and at lunch, he offered me a job heading exploratory research at Polaroid. I said, sir, I'm a medicinal chemist. I'm going into academia. He told me how much he was going to pay me. I said, when do I start? All of a sudden, I'm an industrial chemist. Who would have thought? And so I had this great group of people, and we were inventing all these different things. And you've got to ask yourself, what would a medicinal chemist do at a place like Polaroid? And I came up with something of a weird way of looking at the world. You know, I said, you know, for 150 years of chemistry, of human-designed chemistry, we've done amazing things. We can make the most extravagant of molecules, the most diverse of molecules, but how do we do it? We use high temperature, we use high pressure, and we use these nasty reagents to make molecules that we're very, very proud of. But when you think about it, nature beats us hands down in diversity and complexity, makes far more complicated structures. But wait, it also does it at room temperature, at ambient pressure, using water as a reagent. We're not so cool as humans. After 150 years, we can't touch what nature does. And I looked at that and I thought about it. I said, you know why? Because of our ego. We are so egotistical. We want to make molecules do what we want them to do. We break bonds and we make bonds and we force things to happen. When I would argue nature doesn't do that. Nature sets up systems that allow molecules to do what they want to do. The structure of the molecules is such that they find each other and they assemble each other. Tongue-in-cheek, I call this molecular psychology, okay? If you think about it, when my iPhone comes out of the manufacturing plant, after it cools down, after the volatiles evaporate and the pressure comes back to normal, you can almost hear the inaudible screams of the molecules going, no! They want to go back to where they were before this all started. But if instead, I take a molecule and put it on a couch, and I say, what do you want to do? And the molecule looks up at me and says, I want to be a paint. That's a heck of a paint now, because that molecule is doing what it wants. So I'm being kidding about it, but what I mean by this is looking at the hydrogen bonding, look at the aromatic structure, looking at the molecular structure and correlating it to its inherent tendencies as opposed to making it do what I want to do. And so that's the basis of what Pete referred to as non-covalent derivatization.